Imagine you are sitting in a completely dark room, with only the faint glow from the computer screen illuminating your face, and outside lies the profound night sky, where trillions upon trillions of stars sparkle like diamond dust scattered across an endless black velvet fabric. Every time we gaze up at it, everyone's heart beats just a little faster, because since the 16th century, humanity has ceaselessly pondered the true size of this universe. Ancient astronomers, using rudimentary telescopes crafted from shiny brass, progressively measured ever more distant celestial bodies, and with each measurement, they were left utterly astonished by those immense distances. It is much like standing on a beach and realizing that the horizon is not the end, but merely the beginning of a vast ocean. Our history of exploring the universe is a chain of successive shocks regarding its scale. This realization leads many to question whether the universe is truly infinite or simply so expansive that our imagination cannot encompass it all. Even today, in the year 2025, when technology has advanced tremendously with space telescopes like the James Webb Space Telescope sending back terabytes of data every day, or supercomputers simulating the universe with precision down to individual photons, we still cannot see the entirety of the universe. We know for certain that the universe was born 13,800,000,000 years ago, from that grand Big Bang explosion, and due to its ceaseless expansion, the observable portion of it spans more than 93 billion light-years. Try to picture it. Light from the most distant galaxies takes billions of years to reach us, and during that journey, space itself continues to inflate like a balloon being pumped with air without end. Yet, no one can be absolutely certain that those 93 billion light-years represent the whole. What is the true shape of the universe? Is it curved or flat? Does it have boundaries, or is it an endless expanse stretching forever? These questions linger like haunting melodies in our minds, making anyone who has ever looked up at the night sky feel both insignificant and profoundly curious. Recent observations from the James Webb Space Telescope in 2025 have further deepened this sense of wonder, revealing unexpected discoveries such as the first direct measurements of chemical and physical properties in a potential moon-forming disk around a distant exoplanet, and the detection of phosphine gas in the atmosphere of an ancient brown dwarf named Wolf 1130c, hinting at possible exotic atmospheric processes that challenge our understanding of stellar evolution in the early universe. Allow me to tell you about an idea that completely revolutionized how we perceive the universe, the cosmic inflation model, proposed by Alan Guth in the year 1980. It was a frigid winter evening in the laboratory, with Guth seated at a desk cluttered with papers and equations, when he suddenly realized that to explain why a universe 13,800,000,000 years old is so vast at 93 billion light-years across, and why the density of matter and energy is so perfectly uniform in every corner from the most remote regions just imaged by the James Webb Space Telescope in 2024, capturing thousands of ancient galaxies, formed mere hundreds of millions of years after the Big Bang, we require a phase of super-rapid expansion immediately following the big explosion. That is inflation. In a fraction of a trillionth of a second, space ballooned exponentially, faster than the speed of light by millions of times. Imagine inflating a balloon, but instead of gradually, it suddenly swells billions of times larger in the blink of an eye. That was our universe at that moment. Updates to inflation theory between 2023 and 2025, including studies on warm inflation using standard particle physics particles, have refined this picture, suggesting that quantum fluctuations during this phase could align even better with cosmic microwave background data, while the cancellation of the Cosmic Microwave Background Stage 4 project in 2025 has shifted focus to alternative gravitational wave detections for verifying these models. During that inflation phase, the familiar laws of causality we know, such as a thrown ball following a straight path, utterly collapsed between the farthest points. Space expanded too swiftly, light from one side could never catch up to the other, akin to two people standing at opposite ends of a rubber road being stretched indefinitely. As a result, tiny quantum fluctuations, those random vibrations at the smallest scale of reality, where virtual particles flicker into existence and vanish in an instant, were stretched into enormous irregularities, laying the groundwork for the galaxies we see today. And the greatest consequence: the universe is truly far larger than the part we observe. The latest inflation models from 2023, drawing on data from the Planck satellite and the James Webb Space Telescope, indicate the universe may be infinite, featuring countless separate bubbles. Even if inflation proves incorrect, alternative theories like the flat infinite universe from the lambda cold dark matter model updated in 2024 still suggest space extends eternally. Recent proposals in 2025, such as models linking inflation to entangled qubits in a white hole framework, offer fresh perspectives on resolving long-standing issues like the cosmological constant problem, equating vacuum energy density with observed values in ways that traditional Big Bang scenarios struggle to achieve. Now, envision the universe as a colossal balloon inflating without cease, containing the familiar space with 2 trillion galaxies known through the Dark Energy Spectroscopic Instrument Survey of 2025. The cosmic microwave background radiation, that ancient light from 13,800,000,000 years ago, still enveloping everywhere like a gentle symphony echoing from the Big Bang, is the most vivid evidence. We observe it uniformly from all directions via telescopes like the Atacama Cosmology Telescope, which updated its data this year with higher resolution maps revealing subtle temperature variations that fine-tune our expansion models. But if the universe is a sphere, what does it exist within? The answer lies in eternal inflation. The process never fully halts. In a chaotic inflationary environment brimming with sky-high energy, a small region abruptly erupts into a Big Bang, birthing our universe bubble where energy transforms into particles, stars, and galaxies. Beyond, inflation persists endlessly, spawning innumerable other Big Bangs, each inaugurating a distinct universe. That is the multiverse theory, strongly endorsed by Stephen Hawking in his final years, and now bolstered by string theory with its 11 spatial dimensions from updated M-theory models. In 2025 discussions, physicists continue debating evidence from supersymmetry extensions that could link dark matter detection to multiverse possibilities, though direct empirical proof remains elusive, with quantum experiments like Google's Willow chip sparking theoretical debates but not conclusive validation. Within that multiverse, dark energy, that enigmatic force comprising 70% of the universe, accelerating expansion since its discovery in 1998 and reconfirmed by the Dark Energy Survey and Euclid missions in 2024, serves merely as a variable. In this inflationary region, strong dark energy propels swift expansion, weak causes collapse and dissipation. If you could traverse the multiverse even just in imagination, you would encounter countless versions, some mirroring ours with the Milky Way galaxy and Earth, others utterly alien with bizarre physics. And because it is infinite, infinite copies of you undoubtedly exist, sitting here listening to this tale, with the same cup of coffee on the table. Hard to accept, is it not? Many physicists like Hawking or Brian Greene still engage in heated debates this year at conferences, but indirect evidence from inflation grows ever stronger. Absent a multiverse, some jest that we must resort to believing in a creator who fine-tuned everything to perfection. The Euclid mission's first comprehensive data release in March 2025, unveiling previews of deep fields with billions of galaxies, has provided sparkling cosmic views that sharpen constraints on dark energy density, suggesting its equation of state may evolve over cosmic time in ways that challenge constant lambda assumptions. But the universe may hold even greater mysteries, the simulation hypothesis. With humanity emerging only 200,000 years ago, amid a universe 13,800,000,000 years old harboring 2 trillion galaxies, the probability of an advanced civilization running a simulation of us is exceedingly high. Consider laboratories where we cultivate microorganisms, or futures nurturing entire planets. Earth might be an isolated zoo in infinite space. And if so, those creators would be gods. Recent 2025 analyses of cosmic structure data from the James Webb Space Telescope hint at optimized information compression in the universe's evolution, akin to computer algorithms, fueling speculation that our reality could be a finely tuned program designed for efficiency. Regarding energy, The conservation law indicates the total energy of the universe remains constant, yet accelerating expansion stems from dark energy. The key is vacuum, not empty void but teeming with quantum energy. The Casimir experiment in 1997 measured forces from virtual particles, the Lamb shift refining hydrogen spectrum lines, and spontaneous emission like firefly glow all demonstrate vacuum's baseline energy, potentially the origin of dark energy, a fifth force alongside the four fundamental ones. In 2025, new simulations incorporating these effects propose vacuum fluctuations could drive late-time acceleration more dynamically than static fields. Stephen Hawking, during his 1973 Moscow visit, calculated and was shocked to discover black holes evaporate via Hawking radiation virtual particles at the event horizon, one particle falling and carrying negative energy, causing the black hole to lose mass. Large black holes cooler than the universe's 2.7 Kelvin background absorb cosmic microwave background radiation, but tiny primordial black holes burn hotter, radiating heat and vanishing. The information paradox, whether data falling into a black hole is lost forever, remains a profound enigma, with theories like holography or wormholes to other universes debated fervently in 2025 quantum gravity frameworks. Recent detections of mysteriously energetic neutrinos may trace to primordial black holes' final bursts via enhanced Hawking radiation, potentially reshaping our views on early universe relics and black hole thermodynamics. Now let us draw closer to our solar system. Mercury, the smallest planet, with a diameter of 4,879.4 kilometers, 40% larger than the Moon, nearly 5 times heavier with a density of 5,427 kilograms per cubic meter. It hurtles around the Sun in just 88 days at 175,000 kilometers per hour, 58 million kilometers from the Sun, rotating slowly over 176 days. Temperatures range from -180 to 427 degrees Celsius, the Sun appearing 3 times larger and 7 times brighter. No moons, tilted only 1 to 2 degrees. The Mariner 10 mission from 1973 to 1975 imaged 45% of the crater-riddled ancient surface. The Messenger probe from 2004 to 2015 unveiled a massive core occupying 85% of volume, rich in iron and sulfur, with a weak magnetic field from a liquid silicon iron layer. Ice hides in permanently shadowed polar craters. The Bepi-Colombo mission, launched in 2018, entered Mercury orbit in December 2025, transmitting the latest data on magnetic fields and geology, confirming ancient volcanic activity and solar wind erosion sculpting the crust, alongside refined measurements of the planet's tenuous exosphere influenced by micrometeorite impacts. The night sky conceals giants. Stephenson 218, the largest observed star with a radius 2,150 times the Sun's, luminosity 440,000 times greater, in the Stephenson 2 cluster, discovered in 1990. Positioned 18,900 light-years away in the constellation Scutum, if placed in our solar system, it would engulf Saturn's orbit, its red supergiant envelope pulsing with convective storms vast enough to swallow Earth dozens of times over. The Horsehead Nebula in Orion, 1,500 light-years distant, captured in stunning detail by the Hubble Space Telescope and James Webb Space Telescope in 2024 and 2025, features thick dust veiling background stars, illuminated by IC 434 and Sigma Orionis, spanning 10 light-years while birthing new stars in its turbulent pillars. The James Webb Space Telescope's infrared close-ups reveal the main's ethereal structure, photon-dominated regions eroding the dark cloud's edge, exposing embryonic protostars glowing in mid-infrared hues. Larger structures, the Laniakea supercluster, encompassing over 100,000 galaxies with a mass of 10 quadrillion suns, pulls the Milky Way galaxy at 600 km per second, discovered in 2014 and updated this year with mappings showing its components already fraying under dark energy's relentless tug, foretelling a future where subclusters drift into isolation billions of years hence. And Titan, Saturn's moon, diameter 5,149.46 kilometers, 32% larger than Mercury. Its nitrogen-thick atmosphere 1.5 times Earth's density, surface pressure 1.6 times higher, with methane rain filling ethane lakes and seas 200 meters deep. The Cassini-Huygens mission in 2005 landed, imaging hydrocarbon sand deserts and subsurface salty water oceans 80 kilometers profound. In the future, as the sun swells to a red giant, Titan warms, ice melts, potentially fostering life, a true primordial Earth analog. 2025 studies suggest Titan could sustain minuscule biomass in its ocean, breaking traditional chemistry rules with exotic prebiotic molecules, though Enceladus plumes may offer richer habitability prospects. This universe, with all its enigmas from the multiverse to black holes, from scorching Mercury to frigid Titan, continues whispering endless tales. Each night, as you gaze upward, embrace that smallness and the boundless joy of discovery.